thanks for coming back for our last session now. So right now we'll have, is it Pawel Lichocki? Am I saying that right?
It's almost good, yeah, it's Pawel Lichocki.
Yeah, that's what I said. Cool. Speaking about applied mixed integer programming beyond the optimum.
Yeah. Okay, so can everyone hear me? All right. So hi, I'm Pawel. I'm from Operation Research Team in Google, and today I'm going to talk about applied mixed integer programming. So this is going to be a light-weighted practitioner's perspective on how do we use MIPs to solve real-life problems. So actually it fits in nicely to the previous presentation. It continues on the similar subjects. So the subtitle is Beyond the Optimum to fit nicely within the workshop subject. However, I was actually entertaining a bit of a different twist before the optimum, because the main idea behind the talk is that MIPs are NP-hard, but NP-hard because if you consider looking for the optimum. However, in practice, we almost never care about finding the optimum, about proving the optimum. So this talk is going to be about everything that happens before you find the optimum. So the outline is pretty straightforward. The talk is partitioned into two parts. In the first one, I'm going to give you a practitioner's perspective. Why do we use MIPs? So why are they useful? The intuitive answer might be that they allow you to optimize a system or a product and be more efficient. However, there are many other benefits of using mixed integer programming, and I will be focusing on two of them. One is the engineering benefits, and the other one is that, well, they simply work. And this will nicely lead us to the second part of the talk, which is why do MIPs work? Why can we solve efficiently problems in practice? And at the very end, I'm going to also talk a bit about self-criticism to give you a bit more perspective on the subject so that you can also judge whether everything what I said is true or not. So let's start. So why do we use MIPs? So first of all, how do you solve problems when you're a software engineer? So you have to gather your input, you have to think, then you figure out an algorithm, you implement it, the algorithm produces the output, and this output corresponds to actions in the real world. Now, this is imperative programming because you have to think what you need, and you also need to think how to get it. So you need to order the machine, you need to implement the algorithm. Now, there is an alternative approach of solving problems, which is declarative programming. And here, you do not have to implement the algorithm. You just state what you want. So you create the model. And then there is a black box solver, which is at your disposal, which will solve the model for you. So from engineering perspective, this is a beautiful property because it really reduces the effort for the engineer to solve a problem. So what kind of things we can do with MIPs? So this probably you all know. This is just to ensure we are all on the same page. So this is a MIP, right? You have in matrix form. And this is a standard textbook formulation. You have a vector of variable x. These are non-negative. You have linear inequalities, the constraints. You optimize some objective. And for some of the variables, or all of them, you can specify whether the variables must only take integer values. Personally, I prefer a bit more extended version. These two are equivalent. I mean, the direction of the optimization doesn't matter because minimizing is just maximizing the negative. The offset in the objective doesn't matter because it just translates the entire space. And in practice, you can actually specify the lower and upper bounds for all of the linear constraints and for all of the variables. And by the way, these do not need to be finite. So you could use infinity as the upper or lower bound. So this is what you have at your disposal. And you look at this and you might think, okay, this is not a lot. So what kind of problems can we solve with this? And actually it turns out that there are a lot of practical applications of MIPs. So just to give you a rough intuition how such work is executed. So imagine that you have a knapsack problem to solve, right? So you have items, you have bins, and you have resources. So this is like a multi-dimensional multi-knapsack. And you want to pick items to put in the bins such that to maximize the value. So what is your input? You have the value for each item. Or maybe let me use this. You have the value for each item. You have also the size of each item on each resource. And you also have how big is the bin on each of the resources. So then, of course, for each combination of the item and the bin, you have a binary decision whether to choose it or not. So what kind of constraints you have? Well, for all items, you might pick each item at most once. And of course, every item must fit in the bin. And if you run this, plus the objective, that you want to maximize the value of what you have, this is basically a multi-dimensional knapsack. From the software engineer perspective, this is very short, very succinct, very, very nice. And then what happens is that the client for whom you implemented this comes in and tells you, well, but really we don't need a knapsack. What we really want, it's more like bin packing. So instead of values, we actually have some number of copies for each items, and we just want to find something which fits. So now, if you're a software engineer, you need to rewrite your entire code. But if you're using a MIP, you just change like 30 letters, and it works again. Then, of course, the situation repeats. Somebody comes in and tells you, well, it's not only that we want to place items in the bins, we also want to spread them evenly across different bins. So, okay, nothing simpler. You just add an additional variable, which I call surplus here. The surplus variable will count the surplus of items in each bins. So what is the expected number of items? It's just the sum of all items divided by the number of bins. So this is the expectation minus what you actually place there, and you upper bound it from above with the surplus variable, which you minimize. If you do this, then you will actually find a placement of items in bins which spreads them nicely across different bins. Then somebody comes in and tells you, well, it's not only about the average surplus in each of the bins, we actually care more about the max surplus, so like the long tail. And this is the first objective we really want to minimize. So again, nothing simpler. You add yet another variable, you bound all of the surplus variables with this another one, and you again minimize, you add this to the objective, and now you have two components in the objective, and you differentiate them between them with some sort of high number. You solve this, you have now a nice packing problem, and perhaps at the very last stage, the client comes back again and says, okay, but this is actually a real system which works in real world. So usually we already have some placement. And now what we want to spread the items, but we want to introduce as little change as possible. So again, you just get another data, which is the number of items which are already placed, and you add additional variables which will track the difference between what the solver decides and what was already there. And you add this to the objective, and if you combine this all in 10 lines, you have a model which solves a multi-dimensional, multi-bin packing with balancing of items, with reducing the long tail and minimizing the change with the current state. So all of this means that it's very easy to add new features, and it's a great property of approaching problems. It's very easy to maintain. It's very short. It's very nice. And the language itself of MIPs is very minimalistic because you only have the variables, linear constraints, and the objective, but it's very expressible. I showed you the example of the bin packing, but this extends to many other, like resource allocation, scheduling, anything you think of, you can be expressed as a MIP. So, okay, this would not mean anything if we couldn't really solve the problems, if we really couldn't solve this kind of models that I showed you in practice. So this is a slide I borrowed from Professor Berstmiastock at this year Euro conference. So in the recent 25-30 years, there was a tremendous progress in MIP solving. So if you count the speed up of solvers, there was around 1.5 million times speed up in 30 years. And this does not account for hardware speed up. Hardware speed up is yet another 500,000. So if you combine this all, it's around 1 trillion times speed up. So this means that something that took like a month 30 years ago now takes less than a second. Now, of course, this is averaged, and it's not quite true for all of the models, but this gives you the general idea how much the field has improved. And only because of that, we can actually use MIPs in practice. So how does a typical...
Last question.
Yes?
Has there been as much speed up in non-linear optimization?
This I don't know. So how does a typical progress of solving a model looks like? So this is taken from real data of a model of about 200,000 variables, 50,000 constraints, about 500,000 non-zeros. So the red line is the so-called incumbent. So this is the best solution found so far. The blue line is the bound. So we know that we cannot do any better. And this is yet another nice property of MIPs. They give you the bound. So whenever you have your solution, which is not yet the optimum, you know how far from the optimum you are at the worst case. So this is the time scale here. So usually what you see is that there is some number crunching in the beginning for a few seconds. Then for, let's say, 2-3 minutes, there is a very rapid progress of the objective value, and then it kind of plateaus, and you can even wait up to a day or more to actually prove that what you have is optimal. So that's why I'm saying that we don't really wait for the optimum. So now, this was already talked about in the previous presentations a bit. Assume that the light blue and light red is the less accurate model, meaning that this is the model which was created using less accurate data. Now imagine that you have now the possibility to enhance your model with more accurate data, and then what happens very often is that the actual solution which you get, it gets improved because you have better data, you have better knowledge of your model represents the real world better. So in terms of true objective, you are better off. And the thing is that very often it pays off to work on the model, to work on the quality of data, because this gives you a bigger improvement than trying to optimize to optimality your less accurate model. So in essence, what it means is that data quality or model quality is more important than proving the optimum in practice. However, of course, we still need this very rapid progression, very rapid improvement if we want to have a good quality solution very, very fast. So there is still a question, how can we get the solution of high quality fast? Yes?
How do you measure the quality of the model? I mean, how do you know that when you're measuring the quality of the model on the data that you saw so far, you're not overfitting? And it really reflects the quality of the model for the ongoing or future data.
So this is problem specific in the sense that so the question was how do we assess the quality of the model? So this is, let's say, problem specific. In the end, there are metrics of the system which are not necessarily in the model, but which measure and monitor the system, and which give you an intuition, which give you an idea how well the system behaves. So then if you run your model, if you use one model in your system to produce some decisions, you can watch these external metrics, and then you can evaluate on that. So of course, this does not extend into the future in the sense that if the world suddenly changes a lot, then of course your model might no longer be accurate. But yeah, the running assumption is that if you have a system, it should work in the same way in the future as well. Otherwise, it's not very useful. All right. So we still need MIP solvers to actually find high quality solutions very, very fast. So why are MIP solvers efficient? So very quickly, how does a MIP solver work? I guess that most of you know this stuff. So first, how to solve an LP. So this is the feasible polytope defined by the linear constraints, two variables. So this is the objective. So the objective is contour lines. Thick is bigger value of the objective, thin is smaller. We want to minimize, so the arrow points in the direction. So then the optimum lies on the vertex. There is a mathematical theorem stating that an optimum always lies on a vertex. So how to find this point? Notice that the linear system has infinitely many solutions. It's like the entire feasible polytope. You can fix some of the variables to zeros, which makes the system definite. You solve the linear system, you get some point, which is a vertex. And then there are rules how to change your choice of which variables are fixed to zeros, which basically makes you jump over the vertices up to the optimum. And this is, in practice, this is polynomial. Of course, not theoretically, but in practice, it is. Now, with MIPS, the situation is a bit different because now we're interested only in integer points, so only in these 8 points, and the optimum is here. So, of course, if you solve the relaxation, it's not integer. So how do you solve this? Well, you branch. So you basically do a branch and bound. So you split your problem in two. In this example, you have x2 larger than 3 or x2 lower or equal 2, and you solve the two subproblems separately. Again, the relaxations are not integer, but you can continue. At some point, the relaxation will be integer, and at this point, you found your first incumbent. It's not the optimum yet, the global optimum, but it's the first incumbent. You can prune the rest because you know that no better solution will lie in here, and you just continue branching, and eventually you will find the optimum, the global optimum. So this is how it works. So you have branch and bound. So this is the search tree with some exemplary decision in the beginning. The red ones, so every circle is like a MIP node. The red ones is the infeasible, the orange is the MIP feasible, so it's the incumbent, and then you can prune something out if you know that you can. And in each node you solve a simplex, and that's basically it, right? So this doesn't really tell us why we can solve MIPs efficiently. This actually asks more questions because this is branch and bound. This is like exponential tree search. So why would this work in practice? So yeah. Why this is efficient. So this is efficient. Why this is efficient? We need to go back to our progress plot. There are actually 4 different phases when solving a MIP. The first one is preprocessing, then there is solving the root relaxation, then there is primal heuristics, which has nothing to do with tree search, and then there is finally the tree search. And if you look at the progress, it doesn't always go like this for all of the problems, but it's very, very often kind of like this. That the biggest progress is done by primal heuristics, and then there is still some significant progress done by the tree search, and then it plateaus out in the end. And this rapid progress here is also enabled by efficient preprocessing in the beginning. So there are like gazillions of algorithms that goes into each of these phases. I will just explain some of them very, very, very briefly to give you an idea that a MIP solver is like a collection of different techniques which work together to solve the problem. So preprocessing, so cleanup. So this is the matrix A of your problem. It's always sparse. Like, I mean, in practice, it's always sparse. It's actually very, very sparse, always. It's never dense. So the cleanup, the idea behind the cleanup is to basically it's like syntax analysis of the equations to make them smaller. So you find columns which are proportional and remove them. You find rows which are proportional and you remove them. You find variables which are free and you remove them. You substitute them out, and many, many other things. Eventually, when you do this, after you do this, your original problem from big size becomes much, much smaller. Some other techniques to preprocessing, bound propagation, so you don't need to read this. Basically, for every constraint, you can, every constraint has some bounds, lower and upper bound, but you can also try and infer the bounds from the variables which are in the equation and from the bounds of the variables which are in the equation, and this helps you to make your bounds more strict. There is a lot of literature, especially in constraint programming, on this, how to do this efficiently. This helps because this basically shrinks your feasible set to a smaller one. So you have less to explore. And if you have integer variables, you can also do some rounding up and down to be even more aggressive in bound propagation. Next, there is probing. So probing is a technique where I will present this on the example of binary variables. So probing basically means that you fix the variable to 0, then you fix the variable to 1, you solve the linear relaxation and hope that one of them will turn out infeasible. If this is the case, then you know that the variable has to be 0 in this case, so you can fix it, and then you can clean up the model again and remove it from the model, making it again smaller. And you do it many, many times for many different variables. You do it in the beginning once to make the model smaller. Then there is cuts. So cuts is a very important topic. I will not really talk about it. So cuts, cutting planes, these are equations which you add to your model, which are always valid and which shove off the fractional parts of the feasible polytope. So all of the integer points remain inside, but you get a better relaxation. So like in this example, if you could find these two cuts, you would actually, after solving relaxation, you would be already in the optimum. And there is historically speaking, when cuts were first proposed, they were not very efficient because the way they were computed, they were adding a lot of cuts. And if you add cuts, you make the model bigger because you have more equations in the model. So this has a negative impact on the efficiency. So you have to find a sweet spot. You want to add few cuts which are good, and this is not easy at all. Next, so now, okay, so this was about the preprocessing. Yep.
So when people publish new cuts or whatever, I mean, do they prove theorems saying this is theoretically better than this for some reason, or is it an experimental paper which says in practice?
It's usually an experimental paper, but there is theory goes more like into, let's say, taxonomy, in the sense that people show that, for example, some cuts which were proposed 20 years ago, they're actually members of some bigger cuts family, which could be generalized and parameterized, and then maybe you have a, it gives this more info on how does how could you classify different types of cuts. But I don't think there are a lot of theoretical results which show that, that this cut is really superior to that one. Usually it's going to be superior on some types of problems and not on the others. So most of the paper, in the end, many papers are empirical because they implement this in a MIP solver, try to run it, and then evaluate how it works on a range of different problems.
And the procedures are not complete, or are they?
What do you mean by that?
Like, is it guaranteed to always, it is provable, it reaches the optimum always? Or
cut
procedures?
Okay, I'm not certain about this, but I think that there is a proof that at least for some cuts, you could have an algorithm without the branch and bound, which only bases on adding the cuts, and it is complete. But it is less efficient than the branch and bound. Yeah. So now about the relaxation. So how do we solve the LP relaxation? So this already I showed you, that how to jump over the vertices. So I'm not an expert on this, so I'll just put this very, very vaguely here. Matrix A is sparse, so the entire implementation of the revised simplex relies on that, and it doesn't really make the matrix dense. It always keeps it in a sparse form, and because of that, it's very, very efficient. And also, the other part of the solving the relaxation is that we use so-called dual simplex, which allows you when you explore the search tree and you do the other branch, it's very easy. If you have the relaxation of your parent, it's very easy to find the relaxation of the son. It's just few changes to the basis of the simplex, and you can very quickly get the solution. So this is the reason why, for example, revised simplex, the dual simplex is used in MIP solving in the branch and bound, because it's iterative and you don't have to resolve from scratch in every node. Okay, so this was the preprocessing, then was the root relaxation, and now the primal heuristics. So here are again some examples. So for example, pivot and shift. So this is a heuristic which uses the simplex machinery, but it changes the order of of jumping over the vertices. So the idea is that in the revised simplex, if you push out variables out of the basis, you fix them to their bounds. So if you have, for example, a binary variable which has the 0 and 1 lower and upper bound respectively, if you push it out from the basis, you're going to make it integer because this is the bound. So the idea behind pivot and shift is to make such pivots, such jumpings on the feasible polytope that will actually move not towards the optimum, but towards an integer point. So this will find you some integer point, not necessarily optimal, but it will find you some solution. Another primal heuristic is shift and propagate. So this is very, very easy. It's also called diving. So what you do, you just do branching, and then you propagate the bounds using the very, very simple machinery. You do not use simplex, and you just do this. And then you might end up in an infeasible point. But if you repeat this enough time, there is some chance that you will get to the MIP feasible point, which again is your new incumbent, which you can then use later. Next, there is also a primal heuristic called feasibility pump. So feasibility pump bases on the idea that when you solve the root relaxation, you have the LP feasible point. Now you can round it, so you have the integral point, which is not necessarily LP feasible anymore. So then if you have a procedure to go back to feasibility, you could repeat this loop many, many times in hope that at some point, either this will be LP feasible or this will be integer. So how do we do the rounding? Well, rounding is quite simple. You just round. Very often people add some stochasticity to it, so to ensure that the system does not cycle. And the pump is basically minimizing the L1 norm with respect to the current integral point. And you repeat this, and at some point, this series of LP feasible points and integral points will converge, and you will have a MIP feasible point. So there is also a slight nuance to the method, which was proposed recently. You can also have a different objective where you basically weight in the original objective and hope that you will steer the method a bit towards high quality solutions. All right, so this was about primal heuristics, now about the search tree. So this is pruning. So the value in the node is the value of the relaxation. So here it's 9. The incumbent value is 5. So if you explore in this way, then go back, and you know that the value of the relaxation is 5 here, you can prune the rest of the tree because you know that there can be no better solution than 5, and you already have 5, so it's okay. However, if, for example, here the value of the relaxation was 4, then you cannot prune because 4 is lower than 5, so you have to continue. But do you have to? Well, I mean, you have to investigate the objective. And sometimes you can infer from the coefficients and from the integrality of the variables that the objective, for example, the objective step. So the objective must always be improved in some quantities. So in here, if it's larger than 1, it means that if you have an incumbent of value 5, it means that if you ever find a better solution, the objective must be lower than 4 because the step is 1. So it means that in this case, actually you could prune here. So this again goes into this that you have to very carefully analyze the entire model and infer such information that you can then do pruning more aggressively. Then there's a question of branching. So how to branch? So how to choose which variable to branch on? There are many different methods. The most popular one is probably pseudo-cost branching. So what you do at the beginning, you assume that every variable has, let's say, probability 1 of being branched on. And then once you branch and you have the information about the value of the relaxations, you can induce from this what is the impact of branching on a variable on the value of the relaxation. And you aggregate this knowledge, and then this information steers the selection of which variables to branch in different parts of the tree. Then there is strong branching. Strong branching is usually done at the beginning. So in here, you do not really accumulate knowledge, but you just try to branch on everything. You solve all the relaxations and pick this branch which has the highest value of the objective. And then there is also something that's called active constraint branching, which for each node, when you want to branch, you compute the slacks of the constraints. So this is you check whether the sum of the variables in the constraint is at the bound. If it is at the bound, you say that the constraint is active, and you pick a variable from such a constraint. This kind of makes sense because it means that if you branch on the variable from the active constraint, you're going to force a lot of propagation of the bounds, which will eventually make your search tree less height. Then there is conflict propagation. I think there's going to be some talks about that as well. So when you branch, so this is not the value of the objective. This is like the level of branching 1, 2, 3. When you branch, this actually propagates some bounds and then eventually leads to infeasibility. So you have like a conflict graph. You can analyze this graph, and from this graph, sometimes you can deduce sparse constraints, which you then add to your model, which will help prune more of the search tree in the future. And then there is also the idea about the neighborhoods. So this is like using heuristics inside the search tree. So instead of just branching here, what is done is that you take this node, you convert it to some sort of a sub-MIP problem, and then you resolve the sub-MIP. So again, there are many different approaches. One is called local branching, when you upper bound the Manhattan distance between your current relaxation and the incumbent. Or you can use relaxation-induced neighborhood search, where you actually fix some of the variables to be as in the incumbent and then solve the MIP. This is all in hope that if you do this, you will find quickly a high-quality solution. And finally, last but not least, there is parallelism. So there's ongoing work to make the solvers distributed. So if you have a search tree, you could search one of the branch on one machine and other branch on the other machine. This is now getting momentum, I would say. So to summarize everything, to efficiently solve a MIP, there are just gazillions of different algorithms which goes inside and they cooperate with each other. And all of this works because of the models. So models have a lot of properties which are leveraged by these methods. So models are sparse, there is a lot of symmetries, there's a lot of redundancy in the model, there are some special structures in the model like knapsack constraints, like some subflows and so on. And all of these things, they are leveraged by all of these techniques which are implemented in the modern MIP solver. And what would be nice is to have some sort of more formal approach to this, that we could say that what is the property of a MIP that can be exploited and how, and will it work or not. As far as I know, there are not many, if any, theoretical results with this respect. So just at the end, a bit of self-doubt. So I was talking about MIPs, but are there other techniques to model problems? Well, there are. So sometimes you can model a problem as a graph, and then you have some sort of out-of-the-box algorithms like max flow, min-cost flow. However, very often in practice, what I see is that the problem is almost like min-cost flow. It's like min-cost flow plus some twist, and then this twist is no longer. You can no longer use the min-cost flow. You actually have to resolve to a MIP. On the other regime, you have a more rich syntax languages like constraint programming. So it's kind of like Prolog, you might say. So it has more building blocks that you can use. On the other hand, these, I think, are much less trackable mathematically. So it does kind of seem that that the mixed integer programming, which is in the between, is expressive enough and to be practical and simple enough to be perhaps analyzed theoretically. And then finally, I said that we don't really care about the optimum. Is this true? Well, let's go back to the very first example I gave you, where we were optimizing the multidimensional multi-bin packing. This objective actually spans over 10 to the 6 and 10 to minus 3. So it's like 9 orders of magnitude. So this means that a gap of a very, very small gap might still mean that you have a qualitatively different solution. So in some cases, you actually do want to wait for these bumps at the very end, because this means that your solution is qualitatively different and it's better for you. But that's about it. Yeah, thank you very much, and I'm open for questions.
Great, we have a few minutes for questions.
So I really liked your talk, I liked your presentation, and you made a very compelling case that this declarative nature of MIP is a major advantage, particularly when you have customers, you're dealing with problems that kind of are changed underneath you while you're trying to effectively solve them. So I find this extremely compelling. I'm curious, so I mean, how often in this process does it actually happen that, of course, you can amend the MIP formulation, but then Cplex or Gurobi goes like, just doesn't do it any longer? Because, you know, in our work with MIP, we found that this happens quite a bit, especially when the problem instances get challenging and large. And that what happens then is that people start really looking a lot for alternative models, where in reality, using a different configuration, non-standard configurations of the MIP solver can give you a much easier solution. So kind of two questions: how often does it blow up on you? In your experience, does this happen often? And how do you deal with it when it happens?
Okay, so on the first question, it does happen quite often that the client or the team that we're working with has new features to add. So it's more like that we do not really change the MIP model, we just extend it with additional constraints or change the objective slightly. So this does happen. Usually it does not really ruin the solving. This is case by case specific. Some applications are more let's say time tolerant, in the sense that, you know, if you go from 1 minute to 5 minutes, it's still okay. So you can do this. If this is not the case, because sometimes it's not, sometimes if the new feature destroys your model in the sense that it's no longer being efficiently solved, then you can try to be more aggressive with the reformulation. And then techniques such as like model decomposition works very, very well usually. So very often, you know, we start with one big model because at that point in time it was simple to solve. Then you add features, the model starts being too hard to solve. So then you go back and say, okay, you know, we don't really need to solve this at once. We can like split it and have two different models. First solve that, then solve this. And again, these are trackable and solvable in practice.
So in your experience, you don't fiddle much with Cplex to solve them after all without, you know, decomposition, which can lose you, of course, optimality depending on the scenario.
Yeah, so yeah, we don't fiddle too much with the parameters.
We should probably chat offline.
Yes.
A couple of questions. So one is, if I try to solve satisfiability with a MIP, is it competitive with the satisfiability solver? Yes, I would say not anymore probably. Like the modern SAT solvers are better than MIP solvers at this. Like by a huge factor, or?
I think it depends. Okay, I don't have exact knowledge in my head about this, but I think it depends on the problem as well. And in the end, you know, techniques that the SAT solvers use, they kind of go into MIP solvers. Slowly they diffuse into the solvers. So, you know, eventually perhaps it's going to be competitive anyway.
Okay. So permit me just a quick comment, because I happen to know the answer to that quite well. It's orders and orders of magnitude, and it has been like that for a very long time. So I'm not aware of any practically meaningful or interesting class of SAT instances that a MIP solver could solve, you know, even within a factor of 1,000 within competitive SAT solvers.
Okay. The other question I had was that one could imagine using MIP solvers to do something like deep learning, right? Because you could say that the intermediate layers are binary and then the others are just weights. Has anybody tried that, and is that a reasonable way to do things?
So I don't know if anybody tried that. I would say that it might be prohibitively large. So like in learning, you have a lot of examples that you learn from, and this would, you know, you would have to encode all of that in your coefficients.
One go. I see. There is no batch kind of. I see.
Yeah.
Yeah. Okay.
Question. So how much kind of engineering black art is there in the codes that combine all of these different heuristics and apply them all to a given problem? That is, you could imagine applying one technique aggressively and then the next, or going back and forth and so on and so forth. How are all of these things put together?
Just to, you know, a disclaimer, I did not develop the MIP solver, so this is all that I know by, you know, reading other papers and other work. But from what I know, how commercial MIP solvers are fine-tuned, They basically have a huge repository of all different instances that their clients are solving, and they just run it experimentally with different settings, and then they choose the setting which is the best across some domain or like some problems. So yeah, it's just experimental work.
So from your experience when you were running these MIP solvers, do you, based on your experience, are you able to sort of roughly predict how long it's going to take on some given? I'm wondering whether you see some problem instance and you're able to say, oh, this has certain features it's going to make it take a long time, or oh, this looks like a kind of thing it's going to go quick, or do you feel like you just can't tell until you run it, like this is going to take a long time or quickly, or what that curve is going to look like in a particular instance?
Yeah, so that's a very good question. Yeah, it's in general it's hard to predict beforehand how long it's going to take. Usually I'm positively surprised by the running times. It is sometimes possible to, once you, for example, have the first model, you test it, and then you have the first estimate how it works. Then it might be you might be able to predict that if you add some additional feature to the model, you might have some intuition of how it should affect stuff. So like one of the features of the model is that there are a lot of symmetries usually, so a lot of solutions are equivalent. So then if you add features to the model which break those symmetries, this usually helps a lot. So these are techniques of modeling which you know that they almost surely will help you be more efficient. So there are such things, but in general, I think that we can still craft, malicious MIPs which are very small and which would take, weeks to solve. But in the end, we don't really care that much because these are malicious and we never see them in practice. So.
I can't resist saying, I don't know if Avram was setting me up here, but a substantial part of my talk on Wednesday is going to be exactly about using machine learning to predict the runtime of MIPs, and that is something we can.
Sorry, machine learning to what?
To predict the runtime of solvers for things like SAT and MIP. So we'll for example, talk about being able to, certainly looking beyond size, but looking at combinatorial features of an instance, and within a well-defined distribution, it's quite predictable. And we seem to have wandered off your talk, so maybe this is a good time to wrap up. Thanks very much.
Thank you.